Hello, I'm Andrew, and this is my fifth lab report. So the purpose of this lab was to learn about the application of Faraday's law through observing the behavior after dropping a bar magnet down an aluminum tube. The main models and physical principles are Faraday's law, which is shown here, Lenz's law, which shows that induced current can be created to oppose a change in EMF, Biot-Savart law, which is shown here, Newton's second and third laws, which is F equals ma, and also the equal and opposite reaction, and then magnetic flux and how it can be calculated. So the main preview of my results, so this picture is me dropping down a magnet down a tube, and the computational model of the time it took for the magnet to drop down. My observation time was 1.316 seconds on average, and the calculated time was 1.214 seconds. The main assumptions are air resistance is negligible and only gravity and magnetic force act on the bar magnet, and the system was the bar magnet and tube, and the surroundings were everything else. For the experiment, I used the magnetometer app to find the north and south pole of the bar magnet and dropped it vertically down the aluminum tube 5 times, measuring the amount of time it took between it entering the tube and exiting it. And these are the trial times, and then I averaged it out to get what I got. For the coding, I first started off by putting the measurements of the tube, the foil, and like the bar magnet, and then I implemented the formulas or functions to find the magnetic field of the bar magnet, and then also the magnetic flux. Next, this is for simulating the drop, and that led to these results that I showed earlier. So the main sources of error of this lab are just human error and also an incorrect mu calculation from the third lab, which I used in the code. Additionally, the magnet may have been different from the one used in the third lab, so that could have led to a different mu. The times differ by a little bit, but it's pretty close, and the sources of error could have led to this difference. So some questions. The intensity of the coloring on the tube indicates the magnitude of current flowing through each ring, and red and blue indicate the current flowing in opposite directions. Which color represents which? So I found that red is counterclockwise, blue is clockwise, because using the right-hand rule, this is what was needed to counteract the change in flux according to Lenz's law. As in the result, it was blue, so I used the right-hand rule to find that. It was clockwise. When you flip the magnet around, the currents will be reversed, but the magnet would still be slowed similarly. How does the total time and tube of the real world system compare to that of the computational system? How might the computational system be made more accurate? So the times are pretty similar, but the computational system might have been more accurate because of the human error from like measurement, timing, everything else. And what does the shape of the velocity versus time plot tell you about the forces acting on the bar magnet? So the velocity kind of flattened out inside the tube, so that means that it was staying constant. So that means that the force of gravity counteracted the magnetic force equally and in opposite direction. And outside gravity is the only force acting on it, so it was accelerating. Sorry for the background noise. So the discussion questions: what if the resistivity of the conductor were reduced as close as possible to zero? How would the dynamics of the falling magnet change? So if this were to happen, then the conductivity would be very high due to inverse relation, and this will make the induced current and EMF very high, so the magnet will fall even slower. And what if holes or slots were cut into the tube? How would this affect the ring currents in your model? So if holes or slots were cut into the tube, then there would be less rings for currents to be induced, making the magnet have less resistance while falling, which makes it fall faster. Thank you.